tips for the societal alignment. So without wasting more time, I would like to give the podium to Professor Zhang here. So now is your time we will enjoy your seminar here on the back end. Thank you.
Great. Thank you, Professor Ni, for the kind introduction, and good morning, everyone. So I'm Wenbin. I'm assistant professor here at FIU, which is just next to FIU. So it's my great pleasure to serve you virtually, and I really excited to be here. Today, I'm going to share some of our works stemming from the gap between the design of a fair model in the lab and the real-world deployment. So hopefully, we can have a good discussion. So might not able to see the chat, so feel free to unmute yourself if any questions. Okay, so let's get started. So I think AI is now embedded in nearly every part of life, right? Think of healthcare to assist with clinical prediction, package delivery, automation, and application screening as part of hiring process. So the list for sure goes on, right? Apparently. So these AI systems are powerful and useful. So these powerful and useful systems that do not exist in isolation. So they are embedded actually in society. So algorithms are built on massive amount of data. And that data also become the ground truth for how the AI sees the world. So, but the ground truth is never perfect, right? It can be noisy, it can be biased, also shaped by our human choices. So when these algorithms are applied back into society, maybe whether in hiring, policing, or healthcare, so reinforce the same bias they learned. So that creates feedback loop where biased data leads to biased prediction, which generate more biased data. So they can ask an important question. So what could go wrong when biased AI is embedded in societal system? So the answer is quite a lot, actually. So if the goal of the algorithm do not align with human values, so the output may cause harm. So if the system is applied too broadly without oversight, small bias can scale up to affect thousands or even millions of people. So causing unfair outcomes, injustice, discrimination in hiring, unequal access to credit or healthcare. So here's an example, a concrete example from a report from the Public Republica found that Black patients were underrepresented in clinical care, even when a treatment was aimed at a particular type of cancer that disproportionately impact them. In addition, state-of-art clinical prediction models also underperform on them. So in general, the bias discrimination can be interpreted as a systematically lack of favorism towards one side or another. So I think one might think of the immediate solution could be just to ensure the AI model do not have access to a sensitive attribute, right? For example, the race that we just discussed. So unfortunately, this is not the case, as simply sensitive attribute could correlate with other attributes. So here's another example. It was discussed that Amazon Prime showed the sign of racial discrimination by excluding Black people from service and amenities, although race is blind to this AI algorithm. So in addition, AI bias can be a complex problem which could arise at all stages of our AI-based decision-making, starting from problem selections and all the way to post-deployment. Okay. So other than what we discussed, racial discrimination, AI can be just as biased as human, or even exacerbate all type of real-world disparity, such as gender inequality and age discrimination. Such incidents has therefore sparked heated debate. So pulling scholars from a diverse of areas, such as philosophy, public policy, and law, in addition to computing. So this is why fairness is not just a technical add-on. It requires us to understand how AI interacts with society and how our social structure shape the outcome of the system. Otherwise, if a system is applied without our side, small bias can scale up to affect thousands or millions of people. So to this end, policymakers across the world are also becoming increasingly aware of the issue of AI bias. So for example, US Congress has passed the Algorithmic Accountability Act, which would mandate AI accountability. So this increasing attentive issue has therefore motivated a number of approach. So we can prevent bias, and we call it AI fairness. Okay. So this cartoon briefly documents the history of fairness. So the original fairness research we can see here can date it more than a decade ago. And the trend here is like an increasing trend in the number of papers. So when I was making these slides, my collaborator asked me why this only dated 2017. I think they just like, we don't know how many AI papers we have. So we also lose track on the number of AI fairness papers. But since my collaborator asked me for explanation, I would just say estimate skyrocket somewhere here. And there has been a lot of interesting work done about fairness in machine learning. So although we do not really have a number in terms of publication, so this past decade has witnessed significant advancements on AI fairness. So for example, year 2018, two fairness-oriented conferences were initiated, right? The nice thing about these two conferences are just like AI fairness research, they are interdisciplinary by nature. So we can actually work towards interdisciplinary research rather than multiple disciplines. Later, IBM also launched its AI fairness 360 toolkit. So we can benchmark fair notions and algorithms to help fairness research. So as we previously discussed, US Congress also been trying to pass the Accountability Act to mandate AI accountability. So all the funding agencies has also launched fairness-specific programs and things. For example, this is the NSF 2025 last year SCF Smart and Connect Health program solicitation, which is explicitly identify fairness as a primary research theme. So highlighting its central role in advancing this kind of equitable and trustworthy health technologies. Also, National Institute of Justice predict criminal resolution program, DARPA's AI Forward initiative, so that's national endorsement for the humanity in the Environment Protection Agency, so on and so forth. So all major AI venues also has required to flag ethical concern when reviewing a paper, right? So we can actually make AI for social good. So NIH also launched Of-Us initiative, asking for this kind of nationwide institution and organization to participate to address health disparity. So we are now in 2026. So after all this interesting and exciting fairness research, so where are we at now? So if I were to summarize, AI fairness can broadly divide into two categories. So group and individual fairness. Group fairness asks for parity when allocating favorable outcome across different demographic groups. On the other hand, individual fairness look at individual level, requiring similar individual being treated similarly. So let's take example to have a further look on these two standard type of fairness. First, start with the group fairness. So group fairness originates from a form of disparate impact in legal text. So the commonly used terminology is a sensitive attribute, means the attribute that distinguish favored and deprived community, such as gender in this example. So the most commonly used static parity that I just mentioned, basic test whether the probability of being granted a benefit is the same for both deprived and favored community. So still in this example, we require the probability of granting a benefit, such as maybe critical care resources are the same for both male and female group. So as we can see, this does not meet. As the male granting probability is 100 here, while the female is only 50%. Okay. So in terms of individual fairness, it's stems from disparate treatment in legal text. So the standard notion, fairness through awareness require similar individuals being treated similarly. So here, awareness is the similarity between different individuals. So we require a distance matrix to evaluate the similarity in the input space and another distance matrix to evaluate similarity in the output space. So also need a Lipschitz constant because their input space and the output space are in with different similarity matrices, so we can calibrate the distance between them, okay, in different space. So we can see here, in this example, individual fairness does not hold in this example either, because the upper two individuals are similar in the input space, but receive dissimilar treatment from the AI system. So the same apply to the bottom two individuals. So here comes to the formal mathematical problem definition. So we have dataset D described by a set of features and a corresponding class label Y. So among X, we have a spatial attribute S, referred as sensitive attributes, which define favor and deprive subgroups. So the N here is to train a classifier, so we can infer fairness notion. This notion can be task at hand or specify the practitioners, so we can make accurate but also fair predictions. So apparently in the real world, right, data go beyond this static tabular setting. So for example, data can arrive continuously over time as a string. So this arises a fundamental challenge. Fairness is typically defined at the population level, while in streaming setting, decision must be made sequentially, one instance at a time. So in real world, data also comes in the form of graphs, meaning individuals are connected. So one person's behavior can influence others. We call it non-independent and analytical distributed. So this change how bias and fairness propagate. So this slide highlights another important real-world challenge. So class label can be censored. So such censorship, therefore, leads to this kind of inequitability of what we previously discussed, static parity and fairness through awareness, and more general, existing fairness notions and algorithms, because they assume certainty on a class label. While in censorship setting, class label can be uncertain. So another common assumption of existing fairness method is the complete access to sensitive attributes. So in practice, this assumption often fails due to maybe privacy, legal, or ethical concerns. So this motivate fairness method can go beyond the complete sensitive information assumption. So in the following, I will discuss this new fairness notions algorithm designed to bridge these gaps between fairness research and the real-world deployment. So this leads to the roadmap. I will examine the challenge of operationalizing fairness in real-world deployment, also highlight our work addressing these challenges across different fairness types and the data modalities. I will also discuss the intersection of fairness with areas such as privacy, security, GeoAI, generative models, with motivating examples drawn from applications such as healthcare, housing, and adolescent mental health. Okay, I will start with the first one. How can we address group fairness? Okay, and the data modality is the massive data stream. So this is actually my first fairness project during my PhD. So it's what initially drew me into this type of fairness research. So in streaming environment, data are not static. So each instance arrive on the fly, and they could evolve over time. So this makes fairness particularly challenging because fairness is typically defined at the population level, while in streaming setting, decision must be made sequentially and locally. Okay, so the goal here is fair decision making in this massive streaming environment. So there are various methods to handle data stream. Okay, so one representative online learner is the Hopton tree. It basically scans each data instance only once and maintains sufficient statics at the leaves to grow the tree incrementally. And the key question here is when and how to split a node. So this decision is guided by the Hopton bound using information gain to choose the attribute that best improve predict performance. So however, these splitting decisions are purely accurate driven and do not consider fairness. To address this, we propose fairness gain to measure how much discrimination is reduced by a candidate split based on the task-specific fairness matrix. Conceptually, it basically mirrors information gain, but instead of focus on uncertainty, it pays attention to discrimination reduction. In addition, this information gain falls between 0 and 1 fairness can range from -1 to 1. So negative value basically indicates a speeding candidate increase the bias rather than reducing it, which we should avoid. So building on this idea, fair information gain is proposed by combining accuracy and fairness into a single criterion. So if a spirit does not change discrimination, it will reduce to standard information gain. Otherwise, information gain is scaled by fairness gain. So multiplication is preferred here because we just discussed fairness gain can be negative, and such candidates are therefore disencouraged. So moreover, if information gain and fairness gain, they are not necessary in the same scale. So we can prevent one dominate another. So building on this idea, leads to this type of fairness Hofstede tree, or in addition, this kind of Hofstede, Fahad introduced fair pruning, allowing a node to fairly split uneven the best attributes, significant out from doing nothing. It also maintains lightweight statics, so with negligible additional memory costs, make it suitable for this kind of massive streaming scenario. Okay, so beyond fair information gain and FAT, additional fair information theoretical criteria and a fair online learner with adaptive and customized capability also proposed. So together, this line of work supports fair decision making in this type of massive streaming environment. Now I will focus on the individual fairness instead, and we consider the prevalent censorship phenomenon in real-world setting. So this slide highlights this important real-world challenge. So labels can be censored, yet still informative. That is to say, the true outcome is not always observed. In this example, considering a study on cancer relapse, so whether the event of interest, that is cancer relapse, will happen is unknown for the individual with a question mark here. So we're not sure about his class label, and we call this individual censored. So censoring can occur for various reasons. For example, the study can end while the patient is still in remission. Also, the patient can lose to follow-up during the study, or withdraw from the study, or simply some other reasons. Okay? So such censorship leads to this type of inappropriate of what we previously discussed, static parity and fairness through awareness, and more general existing fairness notions and algorithm, because they assume certainty on the class label, while in censorship setting, class label can be uncertain. So in addition to this kind of clinical prediction, censoring problem also extend beyond the original study medical domain, with example in marketing analytics, recidivism risk entrapment, as their event of interest could be unknown as well. So it's of practical importance for fair decision making in censorship environment. Okay? So formally, this setup we call it censored AI fairness. Since certainty on the class label Y is not always guaranteed, the censored dataset D prime can be further described by the event time and event indicator delta. So when delta equals to 1, the event is observed, indicating certainty on the event or class label. Otherwise, the event time is censored, resulting in uncertainty on the class label. So here, while the class label is censored, it's still informative and essential. So we need to explicitly involve them. Okay. So beyond the censorship that limited the applicability of existing fairness methods, particularly for individual fairness, there's another key obstacle, which is Lipschitz constraint. To understand this, let's take a close look at how individual fairness is typically formulated. So individual fairness typically has two distinct metrics, one to evaluate similarity between different individuals in the input space and another in the output space. In addition, Lipschitz constant just calibrate the distance between them across this type of input and output space. So apparently, such a Lipschitz constant is non-trivial to specify, right? Due to a distant metric difference in the input and output space. And the specification of Lipschitz constant has therefore become another major obstacle for wider adaptation for individual fairness in real-world applications. So to this end, we take one more step further. also to remove the dependence on Lipschitz constant from a ranking perspective. Okay, so specifically, we propose this kind of discounted cumulative fairness to measure whether the model under consideration treats similar individuals dissimilarly amidst the censorship and from a ranking perspective. So the general idea is individuals ranked closer in the output input space should also be situated closely in the output space. So such evaluation is based on whether they are ranking inconsistency in the input and the output space. So we can identify this kind of disparate treatment when allocating favorable outcome. So to quantify such a type of bias, equation 1 is defined, so which further consists of two stages. First, obtain a ranking list based on a similarity matrix. Then we check the ranking consistency between the input and output space. So I will explain a high-level idea behind it regarding how we address this aforementioned two challenges: fairness with censorship and individual fairness without Lipschitz constant. Okay, so start with fairness amidst censorship. So we basically need to quantify similarity between individuals to evaluate whether the similar individuals situated similarly. So how do we achieve this amidst censorship? This is done by the proposed concordance imperative. The general idea here is that similar individuals should be similar in terms of difference between model prediction and actual outcome. So basically, we compare each individual with all other remaining individuals for this difference. So the problem is some individuals are censored, right? So how to compare amidst the censorship? So this is done by identifying permissible pairs from all the pairwise comparison. So what does permissible pair mean here? It basically means among the two individuals for comparison, the shorter time is not censored. All we say is observed. So take this example for illustration. So the event time from T1 to T4 are in ascending order, and X2 is censored. If we focus on the third individual, X3, and compare with other individuals, we have two permissible pairs with X1 and X4, while its pair with X2 is impermissible because X2 has a shorter time and is censored, so we cannot order them. Another example, if we focus on the first individual, X1 instead, again, permissible pair means shorter time not censored. So here all pairs are permissible, including the pair with X2, because X1 has a shorter time and is not censored. So we're able to order all of them. Then among all the permissible pairs, and we look for correctly ordered pair, meaning model prediction match with actual outcome. Still, in this example, the model should assign X1 a higher risk score than all other individuals, including X2, because X1 experienced the event of interest earlier than all of them. Otherwise, model prediction does not match with actual outcome. So with individual level outcomes, concordance imperative is evaluated as a concordance difference between them. Doing so will enable similarity evaluation with censorship explicitly taken into consideration. Okay, so with similarity matrix amidst censorship identified, we further remove the individual fairness dependence on Lipschitz constraint. Specifically, we can now obtain ranking list for each individual based on the similarity matrix. So here, the number of stars correspond to the level of similarity. So then we can look at one individual at a time, checking whether other individuals' relative order to this focus individual are consistent across the input and output space. Okay. Specifically, we project the ranking in the output space back to the input space. Okay. So after such a projection, we obtain two lists in the same space for comparison. So we remove the dependence on Lipschitz constraint. Okay. So then we can compare it with the original ranking in the input space. So we can, by discounting the similarity based on the position, then aggregate for each focused individual, then all individuals as the final evaluation. Okay. So in addition to the discussed censored individual fair notion, a suite of sensor fairness matrix algorithm, also theoretical framework is proposed, so we can explicitly account for censorship. Collectively, they support fair decision making in prevalent censorship environments. So now I will turn to jointly considered group and individual fairness in this non-IID graph structure data. Okay. So first consider the data modality, which is a non-IID graph structure data. So the individuals are connected. Their features and outcome influence one another. This structure is common in real-world abstraction, such as we normally use a social network or mobility systems. And the goal here is to make fair decision-making in this interconnected and non-independent context. Right? So to make this concrete, we can consider graph unit. So basic, just adapt the unit architecture from images to graph. So convolution layers becomes graph convolution layers, and pooling becomes graph pooling. So graph pooling is critical because it selects a subset of nodes to focus computation and improve predict performance. However, this selection setup is exactly where a fairness issue can arise. In this example, so 2 out of 3 orange nodes and 1 out of 2 red nodes are selected during this kind of polling process. So that is corresponding to 66% versus 50%. So we have 16% selection rate difference. So after this unpooling, the information on the orange nodes are largely preserved. However, the red nodes are not. So as a result, the reconstruct graph further disadvantage red group. Okay. So this reflects a clear fairness issue. So concretely, group fairness can be instantiated by selecting compilable portion of the nodes from different groups to avoid systematically underrepresenting certain group during pooling and graph learning. In this example, predictive performance during pooling select 3 out of 4 male nodes, but only 1 from 4 male nodes, violating group fairness. So suppose we try to mitigate this by enforcing group fairness constraint during this time pooling. As we can see, the position of wave 4 and wave 6 are swapped here. However, while this can improve representation at the group level, it also introduces a new problem. So the burden of maintaining group fairness may fall disproportionately on certain individuals. In this example, only wave 4 bears the loss to satisfy the group constraint. So this reflects individual bias, even though group fairness is met. So to meet this joint fairness and individual fairness requirements, we move beyond a single deterministic pooling decision and instead learn a pooling distribution. So like to say, rather than relying on one fixed ranking that unfairly burdens specific nodes, such as wave 4 here, we construct multiple valid ranking. And this ranking also satisfy group fairness as well. So we turn this into a pooling distribution by assigning probability weights to these rankings. So we can form a distribution of post-poll pooling outcomes, and the selection is determined probabilistically. So as a result, expected group fairness loss is distributed equally across all individual nodes, rather than concentrate on certain nodes as training progress. In this way, individual fairness is enforced in expectation while satisfying group level constraints. Okay. So in addition to this individual aware group fairness, we also have work on group aware individual fairness, another way around. So where individual treatment respect broader group fairness and the unified evaluation matrix for jointly evaluation. So together, these efforts surveyed in this paper move fairness research beyond a single fairness perspective. Next, we'll turn to one more real-world challenge in deploying fair models. Okay, so sensitive attribute information is often incomplete. Okay, so this line of work is motivated by our recent collaboration with Florida Department of Health on adolescent mental health. So in which holding fairness is critically important, as social peripheral use are often underflagged despite elevated risk. On the other hand, highly active but non-harmful use are overflagged. So this bias can delay life-saving intervention or trigger inappropriate actions that worsen mental health outcome. However, sensitive attribute information, the prerequisite of most existing fairness work, is always incomplete due to legal requirements or parents do not want to share. So this motivates our recent work on fairness with limited sensitive attribute information. So we begin with a causal analysis that explicitly represents the data generation process. So we consider four variables here: sensitive attributes, so as related features, as unrelated features, and the ground truth label. So here, sensitive related and unrelated attributes are decomposed from the input feature X. So U sub S and U sub S bar are their corresponding latent representations. So the solid arrow here represents the generative process, how S inference feature and label. The dashed arrows represent the inference process, how can we infer S and Y from observed features. So this structure ensures that sensitive attribute inference relies only on related information while maintaining independence between sensitive related and unrelated components. Right? So this causal model then translates to a practical neural network implementation through a encoder-decoder framework with adversarial learning. So the encoder network takes observed features as input and maps them to the latent representation. The decoder network then reconstructs all variables from this latent representation. The optimization consists of two stages. During the maximization phase, shown on the left, two adversarial network, F1 and F2, take sensitive related and unrelated representation as the input, respectively, right? So they attempt to maximize their estimate correlation. This network essentially tries to find any hidden dependency between the supposed independent latent variables. In the minimization phase, shown on the right, the main encoder-decoder network optimized for accurate reconstruction while simultaneously minimizing the correlation discovered by the adversarial network. So this can create a competitive dynamic where the main network needs to learn representation that are truly disentangled. The adversarial network cannot find any relationship between sensitive related and unrelated representation. So with the disentangled representation, we can infer missing demographic using principal Bayesian inference with variation approximation optimized by evidence law bound. So the model factorizes the joint distribution to encode causal relationship between all the variables listed here, okay, while respecting independence assumption. Okay. So finally, this bias mitigation can be performed by enforcing respect fairness notions such as the estimate group disparity defined as here, which basically compares probability prediction disparity between different subgroups. So when we complete the initial implementation and evaluation, we found there were inconsistency between sensitive attributes inference and the fairness evaluation, which was not as we expected. So then we look into this procedure and figure out when performing sensitive attribute and class label inference simultaneously, the model might manipulate sensitive attribute assignment. So artificially reduce the fairness loss. That to say, change sensitive attributes from one group to another while making label prediction. So we call this fairness manipulation. To address this during the training, we prevent the fairness objective from changing how S is inferred. So the inferred demographic probability are treated as a fixed when evaluating fairness. So ensuring the model cannot manipulate group assignments to appear fair. So beyond this limited sensitive attribute information setting, we also study scenarios where such information is entirely unavailable. So this requires unsupervised fair learning rather than what I just discussed, semi-supervised approach. So together, these efforts surveyed in this paper extend fairness research beyond a standard assumption of complete sensitive attributes availability. So now I will briefly discuss the collaborative nature of AI fairness, intersecting with different research domains across a range of applications. Okay, so fairness first has a natural overlap with privacy and security. So machine learning is a representative example, serving as a mechanism to enforce the right to be forgotten, required by regulation such as general data protection regulation. So we need to remove a user's data inference from the trained model. So our recent AI 26 work explores this overlap, highlighting how preserving this kind of privacy can also improve fairness. So fairness also have natural overlap with and is often embedded in language models. Okay, so on one hand, language models can exhibit fairness issues themselves, such as bias representation. On the other hand, fairness-aware methods can also work with large language model to support applications such as policy design, decision support, and responsible governance. So we can help ensure the systems are used fairly in real-world setting. So we maintain a public GitHub repository in this space to support research and community engagement. So more broadly, in generative models, fairness interact with each stage of the life cycle, from training data to generation and real-world use. So shape how these models affect downstream applications. This life cycle perspective highlight the need for collaborative and end-to-end approach to this kind of responsible generative AI, so we can offer broad opportunity for collaboration in both theory and application. Finally, as an application example, so many AI-driven decisions are inherent at location-based, right? Such as ride-hailing, insurance pricing, targeted marketing. So in collaboration with spatial and public policy colleagues, we complete projects on mitigating bias in ride-hailing systems. So with the goal of supporting smart city initiative. So our role takeaway, I'll revisit the evolution of fairness and the current fairness literature. So I try to identify some key gaps between fairness research and real-world deployments, discuss some definitions, algorithms for social goods, as well as the collaborative nature of the fairness. So much of the work presented today is also detailed in this survey paper for those interested in learning more. Okay. So with that, I want to thank my wonderful student, mentor, and collaborator, and colleagues, right, without whom this would not be possible. Also, it has been great fun being here virtually, and thank you all. I'm happy to take any further questions. Oh, maybe did I stop sharing?
All right, thank you for the wonderful talk today. I guess we can just you can either type in or you can just unmute yourself to speak up for the question of our speaker here.
Hi, Wenmin.
Hi, Xinchen.
Yes, thanks for the great talk. So I have a couple of questions. I want your opinion or the feedback. First is, do you know what is the what is the current status of this like a benchmark for the fairness evaluation? Because I think the benchmark itself is very important to drive the research as well as the industry to understand and mutually benefit. That's first. Second, in your approach, you had a solution which is try to map the consistency between the input space and the output space to be consistent, right? I think this is come a little bit contradicting to the machine learning objective because machine learning objective is try to from the data try to find out a portion of the feature space such that the output can be consistent, which is either within the instance or the feature space or finding out the approach to have a subspace to make the samples to be consistent to the supervisions. Right. In this case, how do you comment on this consistency? It looks like you want to force the output to be consistent to the input feature space, whereas the input feature space can be pretty noisy or not a very well informative.
Mhm.
It makes
Yeah.
sense?
Yes, good. The first one regarding the benchmark, we have survey paper, particular benchmark the data set and also the existing matrix in addition to some different method available. That typically will be but you mentioned it's correct in the sense that the benchmark may be still limited in the sense like maybe more advancement will be needed, particularly given nowadays with even targeting multimodality. So this right now the modality is more many like separate in different modality. So this is one thing about the benchmark. I think more effort will be called for along with the recent development in the AI to have across different modalities or multimodality benchmark that will be expected. Currently, most of benchmark are focused on one particular modality, say text, image, okay, or tabular data. So I think this is one thing regarding benchmark. Regarding your second question, for the enforcement between input and output space, there are particular contexts here. We're talking about individual fairness. So individual fairness by definition is similar individual to be treated similarly. How do we define it? Original standard fairness notion is by this type of fairness through awareness. This is exactly to require your output space to align with your input space, which means if two individuals are similar in the input space, they're also supposed to be similar in the output space. So I think this is particular context why we want to enforce in this way. And with simply what I try to do on that part is from a ranking perspective. So we do not need to learn or specify this richness constant, which is not easy to identify because input space and output space are across different domains or maybe use different metrics are not necessarily compatible. And this is what we try to comment. But in a sense, you mentioned about here is because we do want to focus on individual fairness in particular domain or particular context. This particular context require us to enforce similarity obtained from the input space to be preserved in the output space. This is particular context where how we can define or mitigate individual fairness.
Yeah, thank you.
All right, Wenbing, a great talk. I have a very naive question in terms of the group interest, group fairness, and individual fairness here. So, are these two separate problems, or that could be a combined problem where, in your group fairness, that a group of people have some interest, and then another group of people have a different interest, and then you have individuals who have their own needs. I'm not sure if that's something in your consideration or if that's something that people in the community are interested. People have similar interests, people have different interests on some subject, and people share partial interest, something like that. I'm not sure what's the takeaway nowadays in the society.
Yeah, good question. That's exactly, I would say, like the difficulty of fairness nowadays I mean, apparently even different people perceive different fairness differently. So there's more contents to domain specific or the task at hand. If the task right now, let's say earlier days for the COVID vaccination distribution, at the early times, vaccination can be quite scarce. So at that time, we want to focus on maybe group fairness. We want different location, geographical location, have equal access to vaccination. This can be aligned with group fairness. Then later, when we have more vaccination, maybe our focus can be different shift. This is come to the central point is fairness more like maybe different from other computing research topic. It not really have like a scientific yes or no question. It can be domain specific or context specialized. In which context maybe you want to enforce fairness, you will take fairness into group fairness into consideration. On the other hand, if you want to enforce individual fairness, so individual need to be enforced. I also have one work I discussed. So in other scenarios, maybe you other than enforcing group fairness, you also need to take individual into consideration, because while enforcing group fairness, it can be at the cost of certain individual. At that time, you might also want to take them considered jointly. So this is, I would say, more application context specific ones, depending on what your fairness goal is, so you can enforce different fairness notion. I think our work is try to provide different solutions possible for different contexts. So people with different requirements or different regulations, how they can enforce their specific fairness requirements. I hope I answer your question.
Yeah, that is indeed a complete case situation. All right, very good. Is there any other question from the audience? All right, so it's great talk. It's a very new topic in the society. I believe people would see the importance and also the interest over time. So if you have further question or you want to reach out, please reach out to Professor Wenbin Zhang from FIU. With that, I would like to thank our speaker for the wonderful talk today to our audience. I'm going to exit the Zoom now, and happy Friday and have a good weekend.
Okay. Thank you, Ni. Thank you, everyone. Bye.
All right, bye bye.
Thanks, Wenbin.